So based on these experiments, we put together, the behavior of mainly the beginning the forces, but then also we introduced the concept of fields, and we slowly started to develop the concept that the field is something fundamental, the existence of a field, and out kind of this field thinking instead of field equations, the Maxwell's equations, and then we developed the set of mathematics and understanding, including the theorem, but also the Helmholtz theorem for how you could, in general, specify anything. So that's more or less where we were, and then we also introduced the concept of a displacement field and the auxiliary field that basically specifies the response of the field when there's a matter involved. So typically what happens in matter is that there's some sort of screening or some sort of enhancement, and that is encapsulated in this displacement field and the auxiliary field. And so again, we've spent most of last lecture looking at kind of examples, right? So reiterating some of the techniques that we've learned to solve problems, but now in the context of the displacement field and the auxiliary field. And the last kind of problem set in this block is, if you look at it, it's huge, right? It's absolutely humongous. But it's also kind of the crown on everything that you've done so far, right? There are two questions. They look very long. If you really go through it, it's actually okay. It's not that big. It may look daunting, but I want to stress that this is really pulling together everything that you've learned so far, right? How to solve Poisson equation, Laplace equation, and then also kind of what happens in matter. Right? What are the boundary conditions? That's really the focus on the final problem set of this block. Now, this last block, right, the remaining 2 weeks, we're going to talk about time-dependent fields, okay? Because so far what we've considered are static fields, and the generators, the sources of these static fields are so-called, so if I look at static fields, okay? So the sources of static E and B fields are the charge density or the charge and the current density, right? So charge and current. But in particular, for current, we're talking about a steady current, right? So it's a current that always kind of flows at the same rate, and there's no divergence, right? There's no spreading out. There's no, creation of extra charge or charge density, and that's a situation that we're looking to change. And in particular, the first step towards understanding this portion is to understand it in terms of, what is what drives the current through a loop. Okay, so the important question is what drives charges around a wire. and therefore producing current. And in the old days, it's really the concept started around the so-called electromotive force, which technically is not actually force, but okay, we'll call it a force, which is simply just dot dl. So this curly E is the so-called electromotive force. Electromotive force, or simply EMF. I may actually prefer to say EMF because I don't actually have to say the word force, because it's actually what it actually is. Simply, it's a work done per unit charge. In a circuit. Okay, and so some one of the seminal things that Faraday showed in relationship to basically what is driving currents around, and also the consequences of currents are are encapsulated by Faraday's experiments. Faraday's experiments. And in particular, the results were that that the induced EMF is independent of the nature of the wire. Okay, so it doesn't matter, kind of what kind of wire it is, and so on. Okay. The other thing is that found is that the induced EMF is proportional to the change in magnetic field. Induction through the area of the loop, of the current loop. Okay, and so what we're here seeing is so-called Faraday's law, or the beginning of Faraday's law. And so we can understand this by imagining current loop, okay, just some current loop, and there's some magnetic field. Okay. B is some field, and we can have some C, right? This is a description of the loop, and we can specify some small area. So if we define flux of magnetic field, that is basically the number, the amount of field piercing through an area, which in this case, in this picture here on the left, basically is just stating that how many of these field lines pierces through this area A. In this particular case, I've drawn everything in a nice and simple way. So the field is perpendicular to this area, dA. But as you can see, if you write this out in a vector form, you can see that it's irrespective of whether the two things are aligned, as long as I take the scalar product properly. So the scalar product, recall, simply does the projection of the field onto the normal of the surface. Okay, so when we have this definition of the flux, then Faraday's law or Faraday's results basically states that the Faraday's law basically then states that the EMF is proportional to the rate of change of the magnetic flux. So what does this mean? Okay, so that's something that we can specifically take a look at. So again, EMF is given by, if you go back to the first slide, so the EMF here is defined as the work done per unit charge in some circuit. And what Faraday found was that this EMF is proportional to the rate of change of the magnetic flux. What we have is the following result. This is the EMF. Okay. So here, this Faraday's law simply states that the EMF is proportional to the rate of change of the flux, magnetic flux. Okay. Again, the negative sign here is just for the convention and how you define the direction of the current loop. Now, this is something that I can, in principle, I can rewrite. Right? So, in terms of the B fields, I have the result that integral of E dot dl equals to minus d by dt, the integral of B dot A. Okay, then the left-hand side is curly E, is the electromotive force, EMF, and on the right-hand side, I've got the negative of the rate of change, d by dt, of B dA. Now, in this case here, the area is time independent. Okay, at least assuming that I'm not kind of moving around my let's say current loops. Then this area, this B dot A, the area does not change with respect to time. So I could put the d by dt and the integral, I can exchange them. So in this case, I could do the derivative with respect to t first, and then do the integral. And here I go from a full derivative to a partial derivative because B also depends on the position, right? The field depends on, in this case, not just the position anymore, but now also the time. Okay, so now I have this, and really this stress here. I want to stress this. So this result is purely experimental. In particular, the fact that the EMF is proportional to the rate of change of magnetic flux. That part is completely experimental. So even this this expression that we've written down here, again, purely comes from the experiments. And that's really the starting point that we have, right? What we set out to develop in this course is a description of the electromagnetic fields that is completely rooted in experiment, but the description is okay. So let's see if we can turn this into a, a field equation. So let's see if we can turn this into a differential equation as opposed to, or in differential form, as opposed to an integral. Now, I think most of you should have seen this. This may actually be a good time to pause and to give you a little bit of time to think, okay, under the circumstances, how can I turn this into a equation in differential form as opposed to here in this integral? So let's take a quick 5-minute break before we come back. So let's come back at 5:03. Okay, see everybody in minutes. Okay, let's get back into it. I see that Alex has a question. He's asking, can we change the area to demonstrate Faraday's law, given the same field? Yes, that in principle is possible. It would make your life very difficult because you end up um, also having to change, right? It's not only the right-hand side that you end up changing here. You also have to end up changing the left-hand side. You're also changing the loop in which you're integrating over. So, for example, but you could consider an example where you start off with some current loop, or at least some loop, and then shrinking it, and then kind of see what happens with the E field if you don't do anything to the B field. But that is possible. And in a way, we actually will show not exactly a changing area, but when we look at the energy density of a magnetic field, something very similar. The other reason why we typically don't, when we derive Faraday's law, we don't consider changing areas is also because we also end up wanting to write it in a differential form. And so when you consider the differential form, you don't really consider areas, right? You really consider the field and the adjacent points next to the field. And so that's something that we also don't want to, well, it makes our lives unnecessarily complex. Okay, now let's take a look and see if we can turn this equation into a differential form. We've seen this over and over again. There's basically two theorems that we need. Oh, sorry, not two theorems that we need, but two theorems that we typically can use. Do you recall which theorems those are? There's two names associated with it. Anyone? Stokes and divergence theorem, very good. Or Stokes and Gauss's theorem, depending on how you like to call them. So good, okay. So in this case, now that you can either use Stokes' theorem or divergence theorem. It should be fairly trivial, hopefully, for everyone to write down the differential form, right? But in case something that you can't do quickly, let me see if I can convince you. So first thing that we do is, of course, we can write that the E dot dl, and this is using Stokes' theorem that basically says that this equals to the curl of E integrated over some A surface. Of course, this is the surface at which this L here on the left-hand side bounds this A. Okay, but we know that from this slide, we know that this equals to the negative of the integral of partial B over partial T, A as well. So here we have partial B, partial T. Okay, so we can equate the two right-hand sides now, and we can move it to single side. So here we got 0 equals to the integral of now the curl of E plus partial B partial T, close bracket, dA. And indeed, we can arrive at the conclusion that the curl of E equals to negative the rate of change of B. Okay, so of course compare to static case in which we had that the curl of E equals to 0. So this makes sense, right? It's you know, when we talk about static case, this d by dt equals to 0, and so we end up exchanging the relationship for the curl of E to now equals to 0 to now saying the curl of E is some time dependent component. Now, okay, we visualize this field, right? This field is now something that we can visualize, and so imagine that we have some going down or up, it doesn't matter, and you know, I change it over time. Then in this case, how does the E field look? Which direction is the E field? And again, the crucial thing here is to remember, what does the curl of a field mean, and what does the divergence of the field mean? I'll give you a minute to think about it, but in which direction is the electric field pointing in this case? So if I have a B field, you know, pointing downwards, I change it, I vary it over time. In which direction does the E field point? Okay. Anyone want to give it a try? Again, thing to take into account is this equation over here. The curl of E it equals to the negative of the rate of change of B. Anyone? Okay, well, recall that the curl is the component that loops around, so the degree to which there's a vortex, right, going around, and the divergence is the degree to which the field spreads out. And so in this case, Harry is saying in a phi direction, or maybe more simply just, indeed, just looping around, wrap around the B field. Very good, Jeffrey and Harry. Thank you. I know that you can still hear me. Anyway, thank you so much. So indeed, that would be the E field here, and we now have the E field going around like this for changing magnetic field. Okay, so if we take a look at the Maxwell's equations here right now, then you know the set of Maxwell's equations are now this one that we see here, And of course, we have the other set, which is simply given by the divergence of E is rho over epsilon naught. We've got the curl of E, and we have the divergence of B equals 0, and we have the curl of B. Okay. Now, in general, for general situations, a simple an easy way to remember, in which direction the E field is in such a way that it opposes any change, and this is encapsulated by so-called Lenz's law. Lenz's law. And so Lenz's law pretty much states that, when, for example, in a conducting circuit, right, conductor circuit moved, let's say, into a magnetic field, then if conducting circuit moved into a field, then the induced current opposes the motion. Okay, and so this basically states that any changing B field will cause an electric field, which will then be the source of so-called EMF, electromotive force, which drives around the current. Right, that's really where we started off in this entire exploration. And so, in which direction does the E field go? Well, the E field goes in the direction such that it produces a current, which will induce, which will oppose the motion. Because you can think about it in the other way. If it enhances the motion, then you'd simply end up in a situation where I could get an infinite motor, right? I just throw something in, and it just keeps going, right? Because the induced field will enhance the motion, which of course is difficult to do in physics sense, right? We can get an eternal motor. And so in a way, you can also see this as a little bit of form of inertia, right? It's just nature's tendency to oppose any change. Okay, now the important thing to note really here is that all of this, even if I look at Lenz's law, where we're considering, let's say, conducting circuits moved into the field, which then induces a current that opposes the motion, right? But it is important to understand that the electric field, the induced electric field, exists independent of any matter. In this case, the conducting circuit. Okay, so it's not because this circuit exists does the electric field exist, and that's really the change of tone and the focus that we've been trying to do in this course, and that is that the fields are the fundamental thing, or at least that's the starting point. The fields are the fundamental aspects. Okay, now one particular way to look at it, especially if I want to decouple, the notion that there's any matter around for, let's say, Lenz's law to work. Right? suppose that that happens, then we almost end up forced into a situation where we have to kind of add something to it. Okay, and that is, if I look at this set of equations over here, then we end up, realizing that we may be missing something. Because imagine the following, right? Imagine that I'm in this situation over here. Let me draw this again. So let's imagine that I've got some B field. I can't even draw a straight line. A B field, and it ends up inducing some E field. So something here, if I still want to have Lenz's law there, but without necessarily needing, let's say, a conducting circuit, then I must come up with a way in order to oppose this B field. Right? Something there must be there to oppose this B field. And you can more or less kind of guess, especially for those who've taken 2041, you can more or less guess where this is going, right? And this is also to do with parity with respect to the electric and the magnetic field. So one natural solution to this is to then postulate that this E field is then the source of a B field, an induced B field. And if I follow the same kind of analogy, so if I got B and an E, so this E must somehow create a magnetic field that is now in the opposite direction of the original B, the blue. Okay, now how do I do this over a wire like this? Well, I could simply have that. I get a B field that then creates, that loops around like that. Okay, so indeed, so this electric field, this induced electric field exists independent of matter. And so even Lenz's law, so let me write this down. So even Lenz's law should exist independent of matter. And this kind of leads us to a notion of the E field also inducing a B field. Okay, so that indeed this E field then creates a B field that opposes the original B field. And that's really where the basis of kind of the contribution, I would really say, kind of the core contribution of Maxwell. Okay, it sounds a little demeaning because we call these Maxwell's equations, and rightly so, right? Maxwell was the first person to write down the equation in this form, even though he didn't use vector notation. So every equation was 3 equations. But still, his contribution to all of this was also to postulate a so-called displacement current. Okay, and so indeed he asked, does the opposite occur? Does the opposite of a induced E field occur? So in other words, does the rate of change rate of change of the electric field produce a magnetic field. And this is where he came out with the so-called displacement current. Now again, why do we need to write it in terms of a current? And that's because in the old days, we really understood the theory more in terms of charges and currents. And it's really only in the modern times where we shifted the thinking in terms of fields. So that's why still the notion of a so-called displacement current is prevalent, even though you don't really need this concept. So if I introduce a so-called displacement current, it's a partial, we can actually end up with a more consistent set, right? Just this kind of ends up creating symmetry in the equations in Maxwell's equations. And we also see for the conservation of charge. Okay, because the first problem that it addresses is that if I look at this set of equations, over here, then there's some dissatisfactory aspect, right? Because what we have is that a changing magnetic field could induce an electric field, but there is nothing here in the magnetic fields that then corresponds to a changing electric field. And so by introducing the so-called displacement current, we actually alleviate that problem. But actually, a bigger problem that it alleviates is the concept of charge conservation. Okay, so if I go back to my very original concept, so I've got charge conservation. Now, who can tell me the equation that we had originally written down to show charge conservation? Right. So in terms of rho and j, the charge conservation is given by what? Alex is saying divergence of j plus partial time derivative of charge density equals to 0. Very good. So the charge conservation that we started off with is indeed that the divergence of j plus partial rho partial t equals to 0. So this is something that somehow must hold independent of whether we talk about static fields or whether we talk about time-dependent fields. Okay, because this equation simply states that any charge that leaves the surface, right? That's what the divergence basically says, right? So J is the charge, it's the current density, so it's the stream of charge, and if something leaves the surface, it has to have a divergence. If it's a constant stream, then there's the same amount that goes into the surface as that it goes out of the surface. That must obviously be the same as the amount of charge that changes inside this closed surface. But of course, here we've written it down in terms of a differential form. Again, hopefully by now we understand, right? We have enough tools, mathematical tools, to interpret kind of this differential form in this geometrical way. So we have this charge conservation, but And this is a big but, because if I go back to the Maxwell's equations up to here, and in particular, we look at this one. Okay, so the curl of B equals to mu naught J. Now, that equation actually violates charge conservation. Let me show you how. Okay, so if I let's say consider kind of Maxwell's equation for static fields. Okay, now I have that. I write the following. So this is the curl of B equals to mu naught J. Now I take the divergence on both sides. So I take the divergence of a curl, which, if you recall, always gives 0. And the divergence of a curl always gives 0. But this then also equals to mu naught divergence of J. Now this is true, right? Because for static fields, so let me write this down. Indeed, for static fields, indeed, the divergence of J equals to 0, because we end up with constant currents. And so there's no net charge going in or out. That almost immediately implies, some non-static field. So this is fine. This equation is fine for static fields, but we know that the divergence of J need not always to be 0. In particular, that the divergence of J must actually satisfy this thing over here. And so if I want to preserve charge, or the charge conservation law, then so kind of let's see how to write this. Is that the divergence of J is not 0 for time-dependent problems cases. And so we must actually, have something that that is consistent with charge conservation. So we go back to Maxwell's proposal, which is this so-called displacement current. So now instead of just having J, we also have JD, the displacement current, that we add to the total to get the total J. And that we can actually show should work, because now what I have, if I include, so by including displacement current, what do I get? Well, I get that the divergence of the curl of B equals to, we know this equals to 0, but we now also end up knowing that this is mu naught the divergence of J plus the divergence of JD, the displacement current, equals to 0, which is mu naught. And now we've got the divergence of the current plus, now the displacement current is simply given in this equation over here. It's just epsilon naught partial t. So here we've got a divergence of epsilon naught partial E partial t. Now, in this case, whether I take the divergence first or the time derivative, that doesn't matter. These are all partial derivatives. So I can change the order and I can write mu naught. Again, we've got the divergence of J plus now partial by partial T, epsilon naught, and now I've got the divergence of E. And that's something that we ought to recognize because that is simply, if we go to Maxwell's equations that I have here, so indeed the divergence of E is simply rho over epsilon naught. And so in this case, what do I have left? Mu naught, the divergence of J plus epsilon naught drops out because this is rho over epsilon naught. So this is simply partial rho, partial T. Again, must be equal to 0 because of the divergence of the curl is always 0. So indeed, mu naught is a constant. So this now very naturally leads to that the divergence of J plus partial rho partial T equals to 0. This is indeed charge conservation. Okay. So the inclusion of this Maxwell term, okay, this displacement current, actually ends up making our set of equations consistent, okay, at least with charge conservation. Okay, now there is one question that I like to pose before I send you all off on a break. And that is when we consider now, when we also have this displacement current, so the Maxwell's equations are this, okay? So now we have Maxwell's equations. And in particular, we have the following set of equations. So we have the divergence of E equals rho over epsilon naught. We have that the curl of E equals, and that comes from this slide over here. This slide over here is just minus d by dB over d by dE, d by dt. Move this down a little. Okay, and now we also have that. We also have that the divergence of B equals to what now? This is equals to 0. And we have that now the curl of B equals to mu naught J plus mu naught JD, if you will, which you can also write as mu naught epsilon naught partial E partial T. Okay, so that is now the the complete set of Maxwell's equations. Now, I want you to think about kind of this implication in particular. Okay? And this is actually an interesting consideration. What happens if you if you're actually in a situation where we have no charge and no currents? Okay, so completely in an empty space. Okay, but consider empty space. So rho equals 0 and J equals 0. Then we've seen is that this must still hold, but this here, originally we had 0, right? because j equals to 0. Now, in terms of empty space, this line over here and this line over here are both mathematically consistent. Okay, let me quickly save before things go haywire. Okay, that's it. Okay, so we have two equations, two set of equations that in empty space would give a completely consistent kind of a field theoretical perspective, completely consistent mathematically results. Okay, they're both very valid theories. So the thing I want you to think about is why would we favor the top equation, so this equation over here, versus this equation over here? What phenomenon? Again, right? Physics, we have to talk about real life, not just what is mathematically consistent or inconsistent. What is the phenomenon that we end up knowing or thinking that this is the right set of equations as opposed to this here and below for empty space? Okay, I'll give you the break to think about it. Let's take a 5-minute break. So let's come back at 5:46. Okay, see everyone in a minute. Okay, let's get back into it. Sorry about being a bit late. I ran into a student in the hallway, so I had to take care of some little thing first. Okay, so the final topic for today, or the final thing that I want to discuss today, is the notion of magnetic, the energy in the magnetic field. Okay? Now, if you recall, when we talked about the electromagnetic fields, I actually end up showing you the expression for the electric field. Like what's the energy or the energy density associated with the electric field. Okay. And so the question is, well first, okay, let's go. So let's talk about the energy density of fields. Okay, so let's actually now consider the electric field. Okay, so recall, so energy density for E field is given by what? What is the energy or energy density associated with the electric field? Anyone remember? We discussed this in the context of bringing kind of, charges from infinity to create a particular charge distribution. Okay, but instead of actually looking at the charge distribution, we consider the electric field, and we end up deriving a formula for the electric field. Okay, we've actually done it again when we talked about the displacement field. Anyone? Just the electric field. Epsilon E squared over 2. Very good. Okay, so let's say the energy density associated with the electric field is just a half epsilon naught E squared. Okay, again, I can't stress this enough. This is under the assumption that you integrate over all space. Okay? Because we end up in this derivation, we end up canceling a surface term, but only by assuming that we take the surface all the way out to infinity. So this energy density really only exists in the sense of this is the energy density throughout the entire space. Okay, now there is a reason why I haven't discussed the energy density for the magnetic field. Does anyone, well, can anyone guess what the reason is? Okay, the reason is because the magnetic field itself does no work. So if I consider, for example, the force, there's no work, let me put it this way, there's no work on charges. So in our original way, when we considered what is the energy density associated with an electric field, what we did is we considered charges, right, infinitesimally small charges, and we bring them and we stack them to create our distribution. The problem is that the magnetic field does no work on charges, because if F equals QV cross B, then we can see that the force is always perpendicular to the direction of motion. And so in this case, the force is perpendicular to V, or if you will, to L. And so, when work is simply F dot dl for the magnetic field is always 0. So it would have been very difficult for me to consider the energy density of the magnetic field, because in the analysis I would have had to do something where I couldn't just bring some charges over and then consider this. But now we actually have a way of considering what is the energy density of a magnetic field, because now we can actually we can calculate. But we can now calculate the energy needed to establish a magnetic field. Okay, so how much energy does it take to establish a particular magnetic field? So I could get some currents going, and then I can do the consideration there. And that's what we're going to do in the remainder of this lecture, and we're going to see that we're going to arrive at an expression. So I'll actually go all the way to the end. I'll just give you the expression, which is actually an expression you ought to more or less be able to guess, which is that the magnetic field energy density is just a half b squared over mu naught. Okay, so this is the thing that we hopefully set out to prove in the remainder. Okay, so the setup that we're going to consider, the setup that we're going to consider is as follows. So let's consider a kind of a solenoid, but now wrapped around kind of a square faced cylinder. So let me draw the situation out. So let's do, oops, why does this work? Okay. Okay. And so these are the edges, kind of open-ended. So we get something that looks like this, something that looks like this, and then something that goes like this. Okay, let me draw this a little bit better. See, this is why I have relatively awful drawing skills. It's not very helpful. Okay. Yep, that's much better. Okay, so around here, I'm gonna wind, I'm gonna have kind of coils wounded like this. Okay, so just all the way around here. So let's set out the dimensions. Let's make this height h. Let's make the diameter of this thing r. and let's make the width of this thing here W. And okay, so this is the setup that we have, and so now what I want to do, again, imagine this green to go all the way around it. So we got this green going around it like this. Okay, and the first question that I have is, in which direction does the magnetic field point if green has as a current? In the phi direction, very good. Okay, so the field would go somewhere like this. This would be the direction of the field B. And if you imagine this to be a full cylinder, then of course you've got something that pokes out like this. Right? Goes like this. So that's B. Good. Okay, so that's the direction of B. Okay, let's take a look. Okay, so in this case, we simply have the result of a solenoid. So what is the B field given for a solenoid? Well, we know that for a B field for a solenoid is just N is the number of windings, mu naught I is the current that goes through, and then 2 pi R in this case. Okay, and so when we start with this result, we can actually we can step by step go through. Okay, well, how much field is there B inside this system, and can I start from a particular current from 0 and then ramp it up all the way to the full current. Okay, so the first thing that I need to consider is the flux. Again, remember that this is just B dot the area. Okay, in which case, if I look at trying to integrate over this area over here, kind of area like this, then I need to take into account the height, and also integrating R from this point, this is big R, to R plus W. So this here would be N mu naught I over 2 pi times H integral R plus W big R dr over R. Right? Now, of course, we also have N windings. So we need to basically integrate kind of the surface, right? There's N loops around here. So the total flux through this ring is N times, so I'll just write here N squared. Okay, so it'd be N times this result. And so that's why there's an N squared there. Okay, so we're left with an integral of 1 over r, basically, from big R to r plus w. Make this a little bit neater. Goes here. Okay, so the result of integration of 1 over r is relatively simple. So here, so phi b again is given by n squared mu naught I over 2 pi h, okay, the height, log r plus w over r. Okay, again, this is just the result of the integration of this 1 over r. So now I know that the EMF, okay, the electromotive force is just the rate of change, or the negative rate of change of this. So E, curly E, is just minus d phi b dt, which is just negative n squared mu over 2 pi h, oops, or, well, okay, let me write it this way, minus d by dt of this, and you have h, and then the log, sorry, there's an I here, h log r plus w over r. In this case, the only thing that is time dependent is I, right? What we're going to do is going to ramp up I from 0 all the way to some I. So that's the only time dependent quantity here. So we've got n squared mu naught h over 2 pi, the logarithm of r plus w over big R, and then di dt. Okay. Okay, I can put a minus sign here. Completeness. And so the amount of work that I need to do to establish a particular to a particular B field is I can flip the sign back, right? This is the kind of the electromotive force is the thing that then opposes this work. So you know the minus sign is not too important. So now we have the work. So the work done to establish some basically some B is then given by, in this case, this is the rate of work. So the rate of work is just the electromotive force and the bringing in of Q, right, as a change of time. And so in this case, this is just EI. And so here we've got n squared mu naught h over 2 pi, the natural log of r plus w r I di dt, okay, because that's the d by di dt that we've got here. We multiply by I to get the rate of work over time. Now, of course, I could also make a slight trick here and write n squared mu naught h naught 2 pi, and then log r plus w over r. And this portion here, I simply write as d by dt over a half I squared. Okay. So this is the rate of change of work that I need to do, and you know, and since this is the only time dependence here, is d by dt. So the total work is simply n squared mu naught h. And let's see if I did this correctly. Yes. Okay. 2 pi. I'm going to put the half that I got here over here. So I've got this, that, and then let's see, that h, yes, the log of r plus w r here, I squared. Okay, and so actually from going from here to here, the assumption is that we go from I from 0 to I, and in such a way that the magnetic field goes from 0 to B. Okay, so we end up having the expression of the amount of work that it takes us to establish basically the current from 0 to I. And what I want to show that this equals to, taking the field from B to B0, from 0 to B. Okay, and basically we do this by now trying to just integrate over the whole volume. So compare this to the following. So compare this to the following. So the B field is n squared mu naught squared over 4 pi squared r squared. Sorry, B squared. Okay, and this simply comes from this starting point over here. So I've got the B is just n times mu naught I over 2 pi r squared. So here there should be an I squared here as well. Should be I squared here as well. Okay, so what if I try to integrate this over over the entire ring now? So if I integrate over over the entire ring, okay, then I would have something that looks like this, right? If I try to integrate this B field, or B field squared. So let's try to integrate this B field squared over the entire volume of the ring. What do I have? I have that n squared mu naught squared over 4 pi squared I squared, and then basically the integral over some phi from 0 to 2 pi, and then the integral from big R to R plus W. Okay, the H I take out as well. And in order to do this for the whole ring, I have that this is the a small section of the ring, so that's R dr, but I've got 1 over R squared here. Okay, because in this case H is simply built in, right? The H is just simply a constant. And so here what I have for this integral again is just here it's just a 1 over R integral. So I end up with n squared mu naught squared, and this here is 2 pi. So I end up here with just 2 pi below. Let's see, H here, I squared, and again I get the log of R plus W over R. So this is just simply integrating this out over all space, but we've actually seen that the amount of work done, the total amount of work done, is, let me B here, is this expression over here, which up to this mu naught square, mu naught, factor of mu naught, is exactly the same as this here. So indeed, this WB, or actually we wrote this as UB, is just the integral of B squared over mu naught d tau, right, by comparing with W. So in such a way, oh, wait, no, there's a factor of a half as well. Yes, because this here has a factor of a half here. So it would be half here. And so indeed, UB, this is small u, this is big U. Actually, let me not confuse people. Let me just use W here. So small u, which is the density, energy density, is simply a half B squared over mu naught. And again, compare to UE, which is a half epsilon naught E squared. Okay, so we basically have the same pair. Right? So the energy density in the electric field and magnetic field are the same. Okay, or at least the same, a similar expression. Okay, so we have a few minutes remaining. I actually really want to come back to this question here. Okay, we kind of skipped over it, over this question over here. In a sense, right? We have these two expressions that are more or less both valid, right? So this expression, but without the J, of course, or this expression over here. So the question really is, what phenomenon has made it that we consider one thing over the other, consider the top equation over the bottom? And Alex indeed says it's the electromagnetic wave, and that's indeed correct, right? When we look at this expression, this picture over here, oops, where did I draw it? This picture over here, right? So we know, or at least now we know, and we'll cover it in the coming lectures, but the existence of electromagnetic waves basically means that when we have a B field, that should produce an E field, but then correspondingly the E field should produce a B field, even in empty space. But if you don't, if you don't have this system over here, if you have this equation over here, then you would basically end up kind of, there wouldn't be this cycle. So an E field, sorry, a changing B field would generate an E field, but a changing E field would then not generate a changing B field. And so you would have nothing that could then end up propagating of this form according to this picture. Okay, we've got something, and then that creates a changing E field, and then that creates a changing B field surrounding that E field, and something that could propagate. So I just wanted to kind of slip that in. We'll look at it in more detail and more from a mathematical perspective, but from a physics perspective, I hope that it is clear why we do need this set of equation, this one here in the top, as opposed to the bottom one here for free space, even though they're both mathematically consistent. Okay, let's see. I think we've covered most of it. I'm not going to show you the explicit form, the integral form of the of Maxwell's equations. I think those are relatively trivial to to derive. And in any case, I'll show them in the notes as well. So in that case, this is kind of more or less what I wanted to say today. Let me quickly take a question from Punchun Chi. Why is it not U times epsilon d E dt for rho B? What do you mean by U times epsilon? Which U? Oh, mu. Okay. Why is it not mu times epsilon d dt for rho B? Ah, okay. So what I wanted to, so in this expression, this is an incorrect. Oops. Where did I put it? Okay, here. This is what I mean. This is actually incorrect, right? What I was trying to say is that if I look at purely from a mathematical perspective, in empty space, this equation, so this would, in an empty space, let me use a different color. In an empty space, this would be, sorry, this would indeed be this. Right? Mu naught epsilon naught partial E partial T. And so from a mathematical perspective, this equation here in green and this equation here in blue are both consistent, right? They're absolutely fine. There's no mathematical inconsistencies in, you know, if the equations were like this. And so that's where my question came in. It's like, how do we know from a physics perspective that it should be the top equation, this one over here, as opposed to this one over here? And the one hint, and I wouldn't say that that's how we know, but one hint is that in free space, so when there's no rho equals when there's no rho, when there's no j, we could still propagate electromagnetic waves. And you can only do that when a set of equation looks like this and not like this. So this equation here is not the right equation. Okay, so I can now say does not allow for EM waves. Okay, that's pretty much it for today. So let me open up the floor to see if there are any questions, any other questions. Is phi b the flux linkage instead of just flux in a derivation of u b? What is flux linkage? So I'm not very familiar with the terminology. Right, total flux, yes. Yeah, I'm talking because I want to consider the whole thing, right? So if I have this thing wounded around, okay, sorry, my headset is running out. Sorry, my headset is not. Yes, so this is the total flux inside the toroid, because again, we want to consider constructing the entire situation and the energetics in the entire situation. And so again, right, this is a rather simplified discussion, but the same thing holds here. Both expressions only work when we integrate throughout the entire volume. Of course, we're often safe because the field outside. So when we consider, let's say, currents and charges, we integrate over the entire area, but then there's no current or no charges inside, so we can extend arbitrarily the integration through all of space. But for both, the usage must be that you always integrate over the entire space, because otherwise the surface terms. Okay, I don't see any other questions, or at least hands up. In that case, stop the recording.